Imagine the opening shot, a small, misshapen chunk of darkness drifting through interplanetary space. It barely reflects any sunlight, looking more like a piece of charcoal than a shining object of the night sky. For a while, nothing happens. Then, as it falls closer to the sun, the black surface starts to breathe. Jets of invisible gas begin to escape, dragging dust with them. Around the nucleus, a faint halo forms, a coma that slowly grows until this once invisible rock is wrapped in a glowing, ghostly atmosphere. From a distance, it will soon become a familiar sight, a comet with a luminous tail. But physically, what we are really seeing is ancient material waking up after billions of years in deep freeze. We usually treat comets as pretty tails in the sky. In reality, they are time capsules, frozen fragments from the birth of the solar system, carrying ancient ice, dust, and complex organic molecules that predate Earth itself. At the most basic level, a comet is a small icy body that formed in the cold outskirts of the young solar system. Its core, the nucleus, is a mixture of frozen water and other volatile ices such as carbon dioxide, CO, carbon monoxide, CO, and traces of additional gases, all locked together with silicate dust grains and carbon-rich organic material. The proportions vary from comet to comet, but the overall recipe is similar: ice, dust, and organics assembled at temperatures so low that many gases behaved like solids. These nuclei typically span only a few kilometers, yet they hold a remarkably rich record of early solar system chemistry. Unlike planets and large moons, most comets have never been strongly heated from the inside. They did not undergo widespread melting, differentiation, or volcanic recycling. There is no metallic core and silicate mantle separated by billions of years of tectonics. Instead, their interiors remain largely in the primitive state in which they first formed, porous, fragile, and chemically ancient. That is why their composition still preserves conditions from the protoplanetary disk 4.5 billion years ago. The distribution of ices, the types of dust, and the organic compounds they carry all encode information about the temperature, density, and radiation environment where they were born. Because they are so primitive, comets act as chemical archives of the early solar system. Their ices preserve the volatile composition of the nebula from which the planets formed. Their dust records the mixture of interstellar grains and solar nebula material. Their organics trace pathways by which simple molecules in space can be turned into more complex carbon chemistry. When we study a comet, we are not just cataloging another small body, we are reading an original page from the formation history of our planetary system. They also matter for a more personal reason. Comets are potential carriers of water and organic compounds to young terrestrial planets like Earth. Impacts by icy planetesimals and comets in the early epochs of our planet's history may have delivered a portion of the water in our oceans and some of the carbon-based ingredients that later took part in prebiotic chemistry. In this sense, comets are not just distant curiosities. They may have contributed directly to the emergence of habitable conditions on our world. Finally, comets are natural laboratories for studying how ice, dust, and radiation interact in space. As they travel along their orbits, they are exposed to changing sunlight, solar wind, and gravitational tides. Their activity, the way they switch on, flare, and fade, reveals how different ices sublimate, how dust is released, and how surfaces evolve under repeated heating cycles. In this episode, we will unpack that story in detail: how a comet is built, from nucleus to coma and tails, what missions like Rosetta have discovered at Comet 67P Arcturus of Gerasimenko, what comets can tell us about the origin of Earth's water and organic chemistry, and how the different reservoirs of the solar system give rise to short and long-period comets that occasionally visit the inner planets and our night sky. When we talk about a comet, the bright tail is what steals the show. But physically, the real comet is the nucleus, a small, dark, irregular body only a few kilometers across, quietly orbiting the sun for billions of years. Most nuclei are astonishingly black. Their surfaces are darker than fresh asphalt, because the pristine ice has been coated and mixed with complex organic material and space-weathered dust. This low reflectivity, low albedo, is one of the reasons comets look so faint until they come close to the sun and begin to wake up. Inside, the nucleus is a fragile mixture rather than a solid rock. It contains water ice as the dominant volatile, other frozen gases such as carbon dioxide, CO, carbon monoxide, CO, and sometimes methane, CH, and ammonia, NH. Silicate dust grains, from submicron specks to pebbles and boulders. organic compounds embedded in the dust and on grain surfaces. Density measurements from spacecraft flybys and landers show that many comet nuclei are highly porous. Their overall density is often only a fraction of that of solid ice, which means much of the interior is empty space, a loose, delicate aggregate of ice and dust rather than a compact stone. This fragile architecture is why even modest tidal forces or thermal stress can crack and reshape them. Over the age of the solar system, the outermost layers of a nucleus can be processed by repeated passages near the Sun. The most volatile ices are lost, surfaces slump, jets carve pits and depressions. But just below those processed layers, the composition remains remarkably primitive, preserving a record of the temperature, chemistry, and dust-gas mix in the early protoplanetary disk. A comet is not always active. Far from the Sun, the nucleus is just a cold, airless lump drifting through darkness. Activity begins when it moves inward and sunlight starts to warm its surface. At a few astronomical units from the Sun, the upper layers of ice begin to sublimate. They pass directly from solid to gas without becoming liquid. Gas escaping from the surface does not flow out alone. As it rushes through the porous upper layers, it drags dust grains with it, lifting them off the nucleus and into space. Around the nucleus, a vast, tenuous cloud forms, the coma. The coma is a genuine, albeit extremely thin, atmosphere. Its size can reach tens or even hundreds of thousands of kilometers, dwarfing the tiny nucleus at its center. To the eye and to telescopes, it appears as a diffuse glow, because dust particles scatter sunlight, producing a soft, continuous brightness. Gas molecules absorb high-energy solar photons and re-emit them at characteristic wavelengths, creating emission lines and bands that can be detected spectroscopically. In the coma, sunlight and the solar wind begin to reshape the outflowing material. Molecules such as water, HO, are quickly broken apart by ultraviolet radiation, forming radicals and ions. These ionized species are then pushed and guided by the magnetic field carried in the solar wind, setting the stage for the formation of ion tails. The coma is therefore the interface between the solid, ancient nucleus and the surrounding space environment. By analyzing its gas and dust, astronomers can infer which ices are currently sublimating, which molecules are present in trace amounts, and how active the nucleus is at a given distance from the Sun. As the comet approaches the inner solar system, the coma becomes the source of its most dramatic feature, the tails. Despite the popular picture of the tail behind the comet, the physics is subtler and more beautiful. Two main tails form, produced by different processes and pointing in slightly different directions. The dust tail is built from solid particles that were lifted off the nucleus and released into the coma. Solar radiation pressure, the tiny but persistent push from sunlight, acts more strongly on small grains than on large ones, slowly accelerating them away from the Sun. Because the comet itself is moving along its orbit, while the dust is being pushed outward, the dust tail becomes broad and gently curved, tracing a graceful arc behind and alongside the comet. It usually appears white or yellowish in images, because it simply reflects sunlight. The ion tail is a different creature. It is made of gas molecules that have been ionized by ultraviolet photons or by charge exchange with the solar wind. These charged particles feel the electromagnetic forces carried by the solar wind's magnetic field. As a result, they are rapidly accelerated away from the Sun along magnetic field lines. The ion tail is typically narrow, straight, and almost perfectly aligned away from the Sun, regardless of the comet's direction of travel. In color images, it often appears bluish, due to emission from specific ion species such as Co. Sometimes a comet can show multiple tails, fine striations, kinks, or sudden disconnections when the solar wind environment changes abruptly. Over days and weeks, the structure of both dust and ion tails evolves as the outflow from the nucleus fluctuates and the comet's distance and geometry relative to the Sun and Earth change. The layered structure of nucleus, coma, and tails is not just visually spectacular, it is a diagnostic toolkit for decoding a comet's history. Each region samples a different aspect of the same primordial material. The nucleus preserves the bulk composition and internal architecture, which ices are present, how porous the body is, whether it has experienced partial heating or differentiation. By measuring its mass, volume, and rotation, scientists can estimate its density and mechanical strength, which tell us how gently or violently it formed and how many collisions it has survived. The coma is a real-time probe of active processes. The relative amounts of water, carbon dioxide, carbon monoxide, and other gases in the coma change with distance from the sun and even with local time on the nucleus. Dust in the coma carries information about grain size distributions, mineralogy, and the presence of organic coatings. Spectroscopy and imaging of the coma allow us to reconstruct which layers of the nucleus are currently being exposed and eroded. The tails act as large-scale traces of interaction with the sun. Dust tails reveal how much solid material is released and how radiation pressure shapes tiny grains over time. Ion tails trace the coupling between cometary gas and the solar wind, recording changes in the magnetic and plasma environment along the comet's orbit. Sudden changes in tail shape can signal bursts of activity, fragmentation events, or space weather disturbances. By combining these pieces, solid nucleus, gaseous coma, extended tails, missions and telescopes can turn a transient glowing streak in the sky into a detailed physical case study. Each well-observed comet refines our understanding of how the solar system assembled its first solids, how volatiles were distributed, and how fragile, icy bodies evolve over billions of years while still preserving a memory of their birth. When ESA launched Rosetta in 2004, the goal sounded almost impossible: chase a small icy body around the sun for 10 years, match its orbit, go into stable orbit around its nucleus, and then land a probe on its surface. No one had done anything like this before. Rosetta left Earth on an Ariane 5 rocket, looped around the inner solar system using gravity assists from Earth and Mars, crossed the asteroid belt, and finally intercepted Comet 67P Icarium of Gerasimenko in 2014. Rosetta became the first spacecraft to orbit a cometary nucleus and escort it for more than 2 years, watching 67P become active as it approached perihelion and then slowly fade again as it receded from the sun. Its companion, the small Philae lander, performed the first controlled descent and touchdown onto a comet's surface, returning unique in-situ measurements before losing power. Comet 67P itself is a short-period comet of the Jupiter family, with an orbital period of about 6.5 years. It spends most of its time in the outer solar system, far from the sun, preserved in deep cold. Each passage through the inner solar system briefly awakens it. Sunlight heats its surface, ices sublimate, and its coma and tails blossom. Rosetta arrived just before this awakening, which allowed scientists to track, in real time, how a frozen nucleus transforms into an active, outgassing world and back again. For planetary science, Rosetta marked a transition. Before it, comets were mostly fuzzy objects with tails. After it, a comet nucleus became a mapped, geologically complex body with cliffs, plains, pits, and seasonal cycles, something we could study with the same level of detail we apply to asteroids, moons, and dwarf planets. When Rosetta's cameras first resolved 67P, it immediately became famous for its shape: 2 distinct lobes connected by a narrow neck, like a cosmic rubber duck. Detailed analysis suggests that this configuration most likely formed when 2 smaller, independently formed cometary bodies gently merged early in solar system history, sticking together instead of shattering. The result is a contact binary, one object composed of 2 ancient building blocks. Up close, the surface of 67P is anything but smooth. Rosetta mapped towering cliffs hundreds of meters high, circular pits that may be collapsed structures or ancient vents, fields of fine dust, and regions strewn with boulders ranging from pebbles to house-sized blocks. Some areas look like dunes or ripples, sculpted not by wind but by gas jets and the slow migration of dust under weak gravity. Other zones are fractured, with polygonal cracks hinting at thermal stresses as the comet cycles between extreme cold and brief warming near the sun. As 67P approached perihelion, Rosetta watched jets of gas and dust erupt from specific regions, often near cliffs and fractures, when sunlight struck volatile-rich patches. These jets can reshape the surface over a single perihelion passage, eroding cliffs, carving pits, and redistributing dust. Over many orbits, this patchy activity gradually reworks the nucleus, which is why its surface looks layered, eroded, and geologically alive despite the low gravity and temperatures. Rosetta's suite of instruments turned 67P into a chemical laboratory. By analyzing gas in the coma and dust lifted from the surface, scientists confirmed that the nucleus is a mixture of water ice, other volatile ices, like carbon dioxide and carbon monoxide, silicate dust, and a rich variety of carbon-bearing compounds. The dust grains are not just mineral fragments. Many are coated or mixed with complex organic materials, including molecules that are precursors to the chemistry of life. One of Rosetta's key findings was the detection of amino acid glycine and phosphorus, both essential ingredients for terrestrial biochemistry, along with a zoo of organic molecules containing carbon, hydrogen, oxygen, and nitrogen. This reinforced the idea that comets could have contributed not only water, but also prebiotic organics, to the early Earth and other rocky worlds. While 67Ps water itself does not match Earth's ocean water in isotopic composition, its organic inventory demonstrates that cometary material is chemically sophisticated, not primitive in a simple sense. The picture that emerges is of a nucleus whose interior and surface are chemically heterogeneous, pockets of different ices, layers of dust, and regions enriched in particular organics. As 67P warms, some ices sublimate earlier than others, changing the composition of the gas over time and location. Rosetta tracked these variations, turning the comet into a case study of how ice-dust mixtures evolve under solar radiation, and how complex chemistry can arise in deep space long before planets and life exist. By combining the spacecraft's trajectory data with the comet's gravitational pull, Rosetta's team measured 67Ps bulk density to be roughly half that of liquid water, far lower than solid rock or even pure, compact ice. This immediately implied a high porosity. Large fractions of the interior must be empty space. The nucleus is not a solid block of ice and rock, but a loosely bound aggregate of smaller components, essentially a rubble pile of icy, dusty clumps held together by gentle self-gravity and weak cohesive forces. This fragile structure explains many of the comet's behaviors. Low internal strength means that cliffs can collapse easily, pits can form when subsurface cavities empty or ices sublimate away, and the entire object can be reshaped over millions of years by modest internal stresses and external talks. It also means that any future spacecraft that tries to land, drill, or sample such a body must be prepared for surfaces that behave more like compressed snow and loosely packed gravel than bedrock. High porosity and low density also carry a historical message. They suggest that 67P never experienced strong compression or deep melting. It did not pass through conditions that would crush voids or segregate materials into dense cores and lighter mantles. In other words, its interior preserves a record of gentle accretion in the cold outskirts of the early solar system, when small icy aggregates stuck together without being heavily reworked by heat or gravity. Rosetta fundamentally changed how we think about comets. Before, they were often described in simple metaphors, dirty snowballs that just happened to form tails when they neared the sun. After Rosetta, a comet nucleus now stands beside asteroids, moons, and dwarf planets as a complex world with geology, chemistry, and seasonal cycles of activity. We have high-resolution maps of a comet's surface, time-lapse sequences of jets turning on and off, and in-situ measurements of ices and organics that connect directly to laboratory studies and meteorite samples. The mission also refined our ideas about the early solar system. 67Ps fragile, porous structure and chemically rich composition support the view that many comets are relatively unprocessed remnants of the primordial disk. Their ices and organics record conditions that prevailed when the sun and planets were still forming. By tying remote observations of other comets to the detailed ground truth from Rosetta, scientists can now use these bodies as probes of the distant past, moving samples of the environment in which Earth and its neighbors emerged. Finally, Rosetta demonstrated the power of long-term, close-up escort missions. Instead of a brief flyby snapshot, we saw a small icy world evolve over seasons, respond to solar heating, shed material, and then quiet down. That kind of temporal record is essential if we want to understand not just what comets are, but how they change, and how they may have helped shape the histories of planets and, indirectly, the story of life itself. When Earth was young, its surface was anything but blue and calm. The planet was molten, bombarded by planetesimals, and repeatedly resurfaced by giant impacts. In such conditions, a large fraction of any primordial water trapped in the interior or on the surface could have been lost to space through intense heating, atmospheric escape, and violent collisions. Later, during the long tail of planetary formation, icy bodies from the outer solar system began to sweep through the inner regions. Among them were comets, water-rich asteroids, and other icy planetesimals. Each impact delivered not only rock and metal, but also volatile materials, water, carbon dioxide, carbon monoxide, ammonia, and a zoo of other molecules trapped in ice and hydrated minerals. Over tens of millions of years, This slow cosmic rain may have helped transform a once glowing lava world into a planet with stable oceans and a dense atmosphere. For planetary scientists, the central question is not simply did comets bring water, but how big a role did they play compared with other sources? To answer this, we cannot travel back in time, but we can read the chemical fingerprints left in today's comets and in Earth's oceans. One of the most powerful tools for tracing the origin of water is the deuterium to hydrogen ratio, or DOH. Deuterium is a heavy isotope of hydrogen with an extra neutron in its nucleus. Different reservoirs in the solar system, Earth's oceans, various comets, and water-rich asteroids can have measurably different DOH values, shaped by where and how their ice is formed. Measurements of several Oort cloud comets have revealed DOH ratios significantly higher than that of Earth's oceans, suggesting that these particular comets cannot be the dominant source of terrestrial water. Some Jupiter-family comets, originating in the Kuiper belt, also show elevated DOH ratios, although there are a few cases where the values are closer to Earth's. At the same time, certain carbonaceous chondrite meteorites, fragments of water-rich asteroids, exhibit DOH ratios much more similar to ocean water. Taken together, these results point toward a mixed origin. Earth's water likely came from multiple sources: contributions from icy asteroids in the outer main belt, some comets with more Earth-like DOH, and possibly water that was retained from early accretion. Comets are clearly part of this story, but the data suggests they are not the sole or even the primary supplier for all of Earth's oceans. Instead, they act as one component of a complex delivery network that operated over hundreds of millions of years. Comets are not just icy reservoirs, they are rich chemical laboratories. In their ices and dust, spectroscopic and in situ measurements have identified simple organics like methanol and formaldehyde, as well as more complex carbon-bearing molecules. Dust grains can host macromolecular organic material, long, carbon-rich structures that form in interstellar clouds, in the outer solar nebula, or through processing by ultraviolet light and cosmic rays. When such bodies strike a young terrestrial planet, they do more than deliver water. Their impact plumes and surviving fragments can spread organic compounds across the surface and into shallow subsurface environments. In a world with active geology, liquid water, and energy sources such as sunlight and volcanism, these imported organics become raw ingredients for prebiotic chemistry. This does not mean that life came from comets in a direct sense. Rather, comets likely enriched the early Earth with additional reservoirs of carbon-based molecules, complementing organics produced locally in the atmosphere, in hydrothermal systems, or on mineral surfaces. Each cometary impact was a small chemical delivery, and across millions of years, those deliveries accumulated into a substantial contribution to the planet's organic inventory. Because most comets spend the vast majority of their existence in cold, distant orbits, far from intense solar heating, their interiors remain relatively unprocessed. While surfaces can be modified by repeated passages near the sun, sublimation, and outgassing, much of the material just beneath the outer layers still reflects the composition of the region where the comet originally formed. By analyzing the ices and dust from comets, either through remote spectroscopy or by bringing samples to Earth, scientists can reconstruct the physical and chemical environment of the early solar system. The relative abundance of different ices reveals temperature regimes. The presence of specific organic species points to radiation conditions and chemical pathways. Isotopic ratios encode information about mixing between interstellar material and the solar nebula. In this sense, each comet nucleus is a frozen archive. It stores information about the gradients in temperature, composition, and radiation that existed when the sun and planets were still forming. Studying many comets with different orbits and origins allows us to map those ancient conditions in 3 dimensions, turning these small, fragile bodies into one of our most powerful tools for understanding how a planetary system like ours comes into existence. Short-period comets are the regular visitors of the inner solar system. They complete their orbits in less than about 200 years and return again and again, gradually reshaping their own surfaces with every passage near the sun dynamically. Most of them are tied to the region just beyond Neptune, the Kuiper belt and its dynamically excited cousin, the scattered disk. The Kuiper belt is a broad, thick ring of icy bodies extending roughly from 30 to 50 astronomical units from the Sun, starting just beyond Neptune's orbit. It contains a vast population of objects, from dwarf planets like Pluto, Eris, and Haumea to countless smaller icy worlds only a few tens of kilometers across. These bodies formed in the cold outskirts of the protoplanetary disk, where water, methane, nitrogen, and carbon monoxide could all freeze into solid ices mixed with rock and dust. Over billions of years, the giant planets, especially Neptune, have slowly sculpted this region. Subtle gravitational nudges, mean motion resonances, and long-term orbital interactions can gradually pump up the eccentricities and inclinations of some Kuiper belt objects. A fraction of them are pushed onto orbits that cross the paths of the giant planets. Once that happens, repeated close encounters, particularly with Jupiter, can shrink and reshape their orbits until they become Jupiter-family comets, short-period comets with relatively low inclinations and periods often shorter than 20 years. These objects carry the chemical signature of the outer solar system, but their orbital lives as active comets are relatively short. After a few thousand perihelion passages, they lose much of their surface ice, build up insulating dust mantles, and may fade into dormant or extinct cometary nuclei that are almost indistinguishable from dark asteroids. Long-period comets are the true wildcards of the sky. Their orbital periods can span tens of thousands, hundreds of thousands, or even millions of years. Many of them plunge into the inner solar system from highly elongated orbits that come from all directions, forming an almost isotropic distribution in the sky. Their paths suggest a source that is not a flat disk like the Kuiper belt, but a spherical halo of icy bodies surrounding the solar system on all sides, the hypothetical Oort cloud. The Oort cloud is thought to extend from a few thousand astronomical units to perhaps 50,000 to 100,000 AU or more, a region so distant that individual objects are far beyond the reach of direct imaging with current telescopes. According to dynamical models, the Oort cloud began forming early in solar system history, when growing giant planets scattered large numbers of icy planetesimals outward. Some of these bodies were ejected completely, becoming interstellar objects. Others ended up on extremely distant, loosely bound orbits, where the sun's gravity is only barely stronger than the combined gravitational influence of passing stars and the galaxy itself. Over billions of years, galactic tides, close stellar passages, and the slow drift of the solar system through the Milky Way can gently disturb these distant orbits. A small fraction of Oort cloud objects have their perihelia nudged inward, tipping them into trajectories that plunge down toward the inner solar system for the first time. To us, they appear as new long-period comets with very large semi-major axes and orbital inclinations that can point in almost any direction. After one or a few close encounters with the Sun and planets, many are either ejected into interstellar space or their orbits are reshaped, altering whether and when they might return. These long-period comets are therefore emissaries from the extreme edge of the Sun's gravitational influence, bodies that have spent most of cosmic history in deep freeze, only to be briefly illuminated as they pass through our skies. From a dynamical perspective, a comet's visible life as a bright, active object is only a brief chapter in a much longer story. Most comets spend billions of years in distant reservoirs, the Kuiper belt, the scattered disk, or the Oort cloud, on orbits that never bring them close enough to the Sun to trigger substantial outgassing. During this time, they are effectively invisible, small, cold nuclei drifting silently through space. A comet's active phase begins only when some gravitational perturbation, a resonance with a giant planet, a stellar encounter, or galactic tidal forces, alters its orbit so that its perihelion drops into the inner solar system. Once the comet starts to approach the Sun, surface ices warm and begin to sublimate. Gas flows outward, dragging dust with it and building a coma and tails. The comet is now losing mass, its orbit being slightly modified by asymmetric outgassing forces and by encounters with planets. Each perihelion passage strips away a thin layer of volatile material. Active jets can expose fresh ice one season and then become choked with dust the next. Over thousands of or tens of thousands of years for short-period comets, or only a handful of passages for some long-period comets, the nucleus can change dramatically. Eventually, the easy-to-reach surface ices may be exhausted or buried under an insulating layer of refractory dust and rock. At that point, the comet can fade into a dormant state, resembling a dark, inert asteroid. In extreme cases, repeated heating and structural weakening may cause the nucleus to fragment entirely, creating swarms of smaller bodies and meteor streams. So when we watch a bright comet in the sky, we are seeing a transient phase in a much longer dynamical cycle, a brief, luminous outbreath after eons of darkness, and sometimes just before permanent dormancy or destruction. The Kuiper belt and the Oort cloud are not just scenic backdrops for occasional celestial fireworks. Together, they represent the long-term deep storage of primitive solar system material and the outcome of early planetary dynamics. The orbits, compositions, and populations of these reservoirs encode information about how the giant planets migrated, how the protoplanetary disk was structured, and how efficiently material was scattered, ejected, or retained. Because these distant bodies have been kept at low temperatures and largely shielded from intense solar radiation, their ices and dust preserve the chemistry of the early solar nebula with relatively little modification. By studying the comets that leak out from these reservoirs, alongside Kuiper belt objects we can observe directly, we gain insight into the distribution of volatiles, the building blocks of planets, and the processes that shape the outer solar system. Dynamically, these reservoirs also illustrate how the solar system remains gravitationally active on billion-year timescales. The steady trickle of new comets into the inner regions is a visible reminder that our planetary system is not static, but still evolving under the influence of the galaxy, passing stars, and the subtle physics of orbital resonances. In this way, the Kuiper belt and Oort cloud serve as both archives and engines, archives of ancient material and early conditions, engines that continue to feed new comets inward, allowing us to read that ancient record using modern telescopes and space missions. When we look up and see a comet as a bright streak in the night sky, it is tempting to treat it as decoration, a temporary ornament added to the stars. But scientifically, a comet is something far more profound. It is a surviving fragment from the age before planets, a small icy world that never grew large enough to become a planet or moon. Instead, it remained in deep freeze at the edges of the solar system, preserving the raw materials from which larger worlds were built. Comets are leftover building blocks of the protoplanetary disk, mixtures of water ice, carbon dioxide, carbon monoxide, dust, and complex organic molecules that condensed in the cold outer regions around the young sun. While planets like Earth went through violent heating, melting, differentiation, and tectonic recycling, most comets avoided those extremes. Their interiors were never globally molten, their chemistry never fully reset. They are relics of a time when the solar system was a swirling disk of gas and dust, still deciding which clumps would become planets and which would remain small. In that sense, comets act as chemical messengers from a lost era. By sampling their ices and dust, we gain access to conditions in the early solar nebula that can no longer be read directly from planetary surfaces. They also function as potential couriers of water and organics to young rocky planets. Over hundreds of millions of years, impacts by comets and water-rich asteroids may have helped deliver part of Earth's oceans and some of the carbon chemistry that would later participate in the emergence of life. Every time a bright comet appears in our sky, something remarkable is happening in real time. Ancient ice, preserved for billions of years in the dark outskirts of the solar system, is abruptly exposed to intense sunlight. Molecules that have been locked in a solid state since before Earth formed begin to sublimate, escaping as gas. Dust grains that have been buried inside the nucleus since the protoplanetary disk now stream away into space, forming the luminous tail that arcs across the sky. From a scientific perspective, this is a controlled release of history. Spectrometers on telescopes and spacecraft can dissect the coma and tails, identifying water, carbon-bearing molecules, and traces of more complex organics. By comparing isotopic ratios, such as deuterium to hydrogen in cometary water, scientists test models of how Earth acquired its volatiles. By analyzing the structure of dust grains, they probe processes that took place in the solar nebula and even in the molecular cloud that existed before the Sun was born. Each active comet becomes a temporary, natural experiment in early solar system chemistry. Emotionally, the picture is just as powerful. In the glowing tail of a comet, we are not simply seeing ice and dust, we are watching part of our own origin story escape into space. Some of the materials now streaming away from the nucleus are similar to those that once fell onto the young Earth, helping to build its oceans and enrich its surface with carbon. The light of the comet is literally sunlight reflected from matter that has spent almost the entire age of the solar system in darkness. For a brief moment, that ancient material becomes visible, writes a line of light across our sky, and then returns to the cold. In that sense, comets connect the personal scale of human experience with the deep time of planetary formation. A streak that lasts only a few weeks to the naked eye carries information about epochs when there were no continents, no atmosphere like ours, and no life. To see a comet is to witness a tiny, luminous intersection between the history of the solar system and the present moment on Earth. As we step back from this episode, comets stop being background visitors and become central characters in the story of planetary systems. They are small, fragile, easily overlooked, yet they carry clues about water delivery, organic chemistry, and the dynamical evolution of the outer solar system. To fully understand planets like Earth, we must understand the frozen messengers that never became planets but still helped shape planetary histories. The natural next questions lead in several directions. One path looks at impacts and planetary defense. The same bodies that delivered water and organics can also carve craters, trigger climate shifts, and pose risks to modern civilization. Another path explores the physics of comet activity itself, how sunlight, solar wind, and rotation sculpt comets and tails, how repeated passages change a comet from a bright, active object into a dark, dormant core. The overarching message is simple but profound. To understand the evolution of a planetary system, you cannot study only its largest worlds. You must also follow the smallest, coldest, and faintest bodies, the ones that store the initial conditions. Comets are frozen time capsules, and every time one lights up our sky, the early solar system briefly speaks to us in gas and dust.